Okay, we are recording. So, started day 3. So, as I just mentioned a second ago, go to the course canvas and you'll see we're now entering the subject for chapter 3, which has to do with image quality. So, I put together a couple quick slides on there, and probably even more importantly, some MATLAB scripts. So, just download all of those. And this already did that one. All right, looks like I got them all here. So I'm going to start off with the PowerPoint part of this.
Yeah.
All right. So if you looked on the subject area, what we're talking about today is point spread functions, line spread functions, modulation transfer functions, things of that sort. Reading the text will give you a lot of good details, but unfortunately, I think he kind of also obscures the simplicity behind these ideas. Right? So without looking at what I put up here, just has everybody read through or looked through the book yet, or do you not have the book?
My textbook is
It's on the way.
I don't have it yet.
Okay.
Should be here Friday.
So for those who looked at it, could you give a quick statement of what a point spread function is? Like if you were to say this to any other ECE major who hasn't taken this, well, is there a good quick description?
And the reaction to an impulse,
Okay.
or at a particular.
All right.
Probably.
So yeah, that is the idea that's behind there. Does anybody remember the name we give to the response to an impulse function? Yeah, the impulse response function, right? And this is the key thing, right? So this is, if you remember in, if anybody's done controls yet, if you haven't done controls in signals, we talk about this anyway, right? The way in which we describe a function, so we pass an impulse into it, we take a look at the transfer function that comes out of it. Right? Typically, we represent the transfer function in functional space. Right? That's all this is. Point spread function, it's just a single point, how it spreads. So imagine a field of 0 value with one pixel that's has a single, value of 1, and then you image it with your system. Right? Now, pretty simple idea. Right? We'll see in a little bit that it actually doesn't work that nicely. Impulse response is actually not a particularly favored thing within here, mainly because the point spread function is going to turn out to be very hard to actually, in practice, capture. I'll show you why. That's what one of the MATLAB scripts will help you do, is to see why that one stinks so bad. And better ways to get at the same exact idea, right? And that's really where the line spread function. There's another one the book doesn't mention called an edge spread function, which is actually the one we use. But we use the edge spread to get the line spread. And then we just use the line spread. So in practice, that's what really happens. The book is going to play pretty strongly to point spread, and the reason they will, you can go between line spread and point spread. It's really easy to go from point spread to line spread. You can go backwards. It's simple when it's a symmetric function, right? The same in all directions. If it's not, like if it's an oblong one, it'll turn out you can still do it. You just have to take the line spread from multiple directions. And then you can back project and figure out. Some of the techniques we'll talk about later will actually show you how to do that. So from our terms, we're going to consider point spread and line spread basically interchangeable because you can go between them. Not that they are the same. There's a lot of similarity. They are tightly related, and you can go back and forth as necessary. In practice, most people just deal with line spread for some stuff we're going to see later. All right. Now, the one you're going to really see a lot of, if you do literature, if you ever go out and work in the field, even if you just do camera optics, you're going to see MTF, modulation transfer function. And this one is talked all over the place. It is like the one everybody wants to get. And there's a practical reason for this. So if I were to take that point spread function, the impulse response, and I were to take its Fourier transform, right? We had said the Fourier transform or the impulse response is just the transfer function, right? Well, it's called an optical transfer function for us, dating back to cameras and everything else, right? So that is the Fourier transform of the point spread. If I were to take the magnitude of the point spread function's Fourier transform, right? The magnitude of the transfer function, that is the modulation transfer function. Right? So the MTF is just the magnitude of it. It is more difficult to get the phase, and for purposes of resolution, we only need the magnitude. And most of the time, people are just asking about magnitude. So what we usually care about is the MTF. Right? You can do an awful lot of stuff just knowing the MTF. If you were to add the phase information back in, then you'd have the full transfer function. Now, very often, we're not actually concerned with applying the transfer function. That may seem a little bit weird, but think about it this way. What does the transfer function describe? Even just the optical transfer function.
The frequency of like how often you have an impulse, like in the time domain.
Okay. So it's taking in essence and telling you something about those particular, the frequency response, right? How it's going to attenuate a signal, because in most cases it's not going to amplify, right? So, but it's talking about attenuation of the signal in the frequency domain by frequency. So if I were to apply that to an image, I would get what your medical system is going to generate. Now, do you have another way to get what the medical system will generate? Yeah, just take the picture, right? So this is telling you kind of mathematically, we need this to go backwards, but we almost never go forwards unless we're just simulating something to generate a phantom. And we will do that sometimes, right? So there is some use to it, but just think of it in this terms, right? Our big concern is figuring out how do I clean this up and go backwards. So knowing how different frequencies were attenuated is actually often all you need to know. So it is very helpful for the part that we need. All right, so I mentioned the line spread function. So if you think a point spread function, it's a single point and it goes out. One of the reasons this is difficult is how would you actually build that? Imagine for a sec, I wanted to take an X-ray and I wanted to take the X-ray of a point. How do I get a point to float in space so I can take an image of it? Maybe I can get magnetic fields and suspend it, but that might deflect my X-rays, right? I mean, because really to get a point, it's got to be towards the center, and it's got to just be a point. Maybe I could find some translucent material or truly transparent material and suspend it in that. But it's getting kind of difficult to figure out how do I actually make a true point that I can take an image of. Is it possible to make a really easy, cheap system to image a line?
A string.
Yeah, yeah, string or a wire, whatever material you want, suspended above and below, you've got a straight line coming in. It's easy to take that. So the first thing, just practically speaking, for us, it is really difficult to come up with a way to generate a point. The one case I know somebody's done an optical one, you could sometimes just put a picture up on the wall with a single dot. It's harder on medical imaging areas. You can put little tiny things, like I said, inside a transparent material. If you look at this from satellite perspective, they've sometimes actually put out these type of patterns on the ground and putting dots. But then you have to be careful, the dot has to be big enough to be seen. So you have to have some knowledge to set it up in the first place. But anyway, so generally speaking, a point is just going to be hard to build. So a line is easier. If you think about it, a line is just a whole series of points though, right? So if I were to take that point and I were to just integrate in one direction, let's say y for a vertical one, why might I want to do y instead of x for my line? Sag, exactly, right? The gravitational field means I get a straight line this way, but I don't get a straight line this way. And that'll influence things negatively. So we often do just a vertical one. So I'll take that point spread and I integrate from minus infinity to infinity in the y direction, or if you're doing it digitally, you just sum up the columns, and you've now turned your point spread into a line spread. So it is trivial to go the one way. Like I said, you can cut a profile and reverse it from the line spread if you wanted, provided it's symmetric. And if it's not, multiple line spreads. The other one that's out there, I mentioned the modulation transfer function. What we will often do is actually put this, instead of in terms of the Fourier transform of the point spread, it'll often be defined as from the Fourier transform of the line spread. So I just noted that here. The book has a weird notation for it. They use capital L to be the Fourier transform of capital LSF. So you just have to know that. So I just tried to put a little bit explicit here, right? F for Fourier. This is in PowerPoint, and I tried to get their stupid thing to give me a calligraphic F so it looked like the Fourier transform. And after 5 minutes of trying to get them to change their font, the second I told it was equation, I had to find the special symbol in amongst something. It wouldn't let me just change the font. So it was like cursives. Right, so just imagine that was a cursive F, right? So I'm saying take the Fourier transform of the line spread factor function and then evaluate it at F, right? Because you have to put the evaluate part outside the transform area. And then the same thing, take its absolute value, and then we normalize it. This is really important, and it will play up in some of the homework areas. We always normalize it so that your basically your constant at 0, it should be equal to 1. And everything is relative to that. So in essence, the modulation transfer function always, always, always should be 1 at the constant at frequency 0. That make sense? That does, like I said, it will play up in the homework. The homework for 3 should be pretty straightforward for most of you. At the end of the day, you ought to have no problem doing them. You and MATLAB should get it done in like half an hour to an hour if you sit down and just do it, which would be my suggestion. But you can do what you want. All right, do we feel comfortable with the basic definitions here? All right, I'm going to give you the formal definition of modulation transfer function. Now, I know at least one. Has anybody ever taken a look at some biomedical instruments, that sort of pulse oximeter stuff?
Yeah.
Uh, If you look at those, when we check out these type of signals, right, we will often pass light through, and we want to see what the attenuation is. And then what we measure is we're trying to see how when your blood's passing through, how does it change things. So what we'll do is we'll measure it over time, and we'll see, you know, fresh blood comes in, and it'll change the absorption because oxygenated blood absorbs light differently than deoxygenated blood. So you'll get this time varying signal. And what you'll do is you'll measure the difference between the highest and the lowest point in your time series for the light that gets through, and divide it by the DC value, the midpoint, right? And so if you think about the AC value is the largest minus the smallest, that's the spread of it, and the DC is the largest plus the smallest divided by 2. But very often we don't like to divide by 2, right? And usually the AC is pretty small compared to the DC component, so we typically don't worry about that, you know, type of area, because the difference is often negligible when you're looking at them. For a lot of ours, when we run these, the difference between the AC and the DC, they're going to get attenuated quite a bit, so it'll be very similar. In any case, we're going to take this and divide by 0 anyway, so the factor of 2 will drop out later. So it's also irrelevant because of the later normalization factor. So we just do max minus min over the sum. And you can think of that as the AC value divided by the DC value, right? At that particular point. Does that make sense? All right, so that is how we measure the modulation, right? How much does it vary? And we'll show you what we're going to do for these. Usually what this is we'll give you some line pairs. And so there'll be a light band and a dark band. And when you kind of blur them together, they'll knock each other out, right? The dark part will pull the light down, and the light part will pull the dark up, and you get this kind of gray part. And if the blur is big enough, you just can't tell the difference, and they're all the same. So what you're doing is you're seeing how much, right? The light part is your high value, the dark part is the low value. The difference between them, that's your DC. Once you have calculated that, and you do that calculation at every frequency, i.e. you just do it at a whole bunch of line pairs. All right, so you try it at a line pair of 2 millimeters, and so on and so forth. Now, when I say line pairs, does that make sense? So what do I mean by a line pair?
Just the 2 values you compare.
Yeah, light and dark. Why do I call it a line pair? Why? I mean, we don't use these type of terms normally when we're doing signals and electrical, right? So, right, if you think about it, I've got a light band and a dark band. What's that trying to approximate that you normally get with a signal? Yeah, how much of a sine wave?
1 period.
1 period. So this is 1 period of a square wave. Right? Why don't we do sine waves? Don't sine waves have a lot of advantages? Yeah, they have huge advantages, right? So why don't I use them?
It's more complicated. You need more lines.
Yeah, think about how would you build that? Very often the way you're going to get, like for x-rays, I can't just paint things, come into light paper and just paint, a dark line on it. What I have to do is I have to have material that basically does not resist the photons passing through and ones that do, and I have to machine it. So if I want to get a sine, I would then have to basically machine that pattern of a sinusoid precisely at a bunch of different sizes. That'd be crazy expensive, as opposed to making a square block and just stacking them. Right? So again, we've switched from a sine to square waves for the pure factor of cheapness and buildability. But it's not going to change. Right? It will have some implications to us, but that's going to be what the real big key is going to be. And then we'll just measure it a bunch of sizes, see those differences, and away you go. That is a practical thing. So MTF is really easy to measure. Okay? We'll take a look at a bunch of different phantoms that are designed to do this, but that is something, it's the magnitude of my transfer functions, tells me how my system operates. I can just measure it by just machining a couple blocks and sticking them next to each other. And we'll show you even some better ways than just the line pairs too. All right. Now, we talk about resolution quite a bit. The book is gaga over full width, half max. In truth, it is all over the literature. It's becoming less and less popular. All right? Now, there's a practical reason for full width, half max, which essentially, we're going to take a look at this as another one of our kind of MATLAB example codes. We'll see why this looks. But think about the idea, right? If I were to take some type of a signal, here I'll just draw, we'll see this in the MATLAB code. But imagine I just took a pulse of some type, right? And I found wherever it's half size. Right? So I take the mat, I go down to the halfway point. I cut across at that area, and I measure what is the width. That's what it is. So usually this is done on the point spread function. You can also do it on the line spread function. You just take a pass through it, you find the maximum point of either the point spread or the line spread, you go down half it, cut across, it's a spatial, both of those are spatial domains, and it basically tells you how wide that is. The reason why you care about it is imagine I had a second one. This is the mid area. This distance, if I took this side here and plotted it on the other one, so they overlap each other, right? So I took this point here, moved it here. Does that make sense? And then I added these two together. This would go up to the full height limit. This, if I had a signal that dropped off to 0, would leave this at full height. So it would be kind of hard to tell. There'd be some variation possibly, right? Assuming again I get to 0. That's not always true, right? But assuming I got to 0 there, it would in essence give me something pretty close to a straight line, and I wouldn't be able to tell that those were two separate things. That's the original motivation behind full width, half max. And turns out it doesn't do that except for special functions. It gets close. So it's an approximation. So that's why they want the full width at half, just so they can do that. It's how close two different points can get and still be distinguishable. Does that make sense? Yeah.
In the second line under full width half mass, the IF of NCF of X 90.5, does that impulse that you're drawing there have to be centered at DC?
So in general, we're going to assume that we are shift invariant.
Okay.
For most of our functions.
Okay, great.
Right? Now, if it's not shift invariant, a lot of the nice stuff here goes away.
Okay.
And there are some cases. So that's why in the first homework, which is actually on chapter 2, we do have you check is something shift invariant. The majority of medical systems out there are shift invariant. Right? That doesn't mean you will always get one, but in general they are, so therefore it's kind of nice. And the trick to this one is just remember, MTF is in the frequency domain, so IF is the inverse Fourier, and again, I can't do F minus 1, and they won't give me script. So imagine that's the inverse Fourier transform of your MTF,
Okay.
right? And then you set that equal to a half, right? And then find whatever that x0 is.
Okay.
That is the distance from the center of your spread to the edge at height half. But you need two of those.
Okay.
So you multiply by 2.
Great. Yeah, I was thinking that spread is in the frequency domain. So.
Yeah, that's why the IF, the inverse frequency.
Thanks.
And if you read, they do give an example, and they will, they actually do mention take the inverse Fourier transform, but they mention it really quick. If you're not paying attention, it's easy to miss. But you're absolutely correct. Now, the rest of these resolutions here, this is going to be calculated in the frequency domain, which means you're going to get 1 over that resolution. And then it's implied that to get the resolution, you have to invert. Okay. So, but all the other resolution ones down there will be on that. Anyway, we feel good so far. Okay, so full width half max, it's a really straightforward concept. And it turns out it is not necessarily the best one, which we'll see some examples of why that's the case. Very common resolutions that we do to actually get this more directly will be either 3, 5, or 10%. Like some people will talk about MTF 50, but the 50% line, but that is not a good measure. Right? 3, 5, or 10 is actually the best measure you can get. And 1 over whatever that frequency is, you don't have to multiply by 2. It basically is finding that distance over here. But it allows you, whereas with the half max, it assumes the tail drops off quick enough, but it doesn't guarantee it. And when it doesn't drop off quick enough, it's high and you'll get a peak on the other side and it'll still create a trough, which will let you distinguish them. And if it drops off too fast, you'll get kind of like bright spot, bright spot, bright spot with something in between and you'll get a false image overlap. So there can be a lot of challenges actually with full width half max. Right? Whereas if you aim it such that the part down here is hit 0 or is close to 0, and that's what those ones are trying to get at, you'll get an idea much closer of the actual distance to separate them out. So you literally just take the MTF, find the frequency that it's equal to one of those values, and then 1 over that. And that'll give you your resolution size. So it's a very straightforward calculation. The Raleigh limit for these gives you 0.09. So if you use the basic Raleigh limit for optics, now it turns out the Raleigh limit is a little bit over conservative in most of our cases. Right? That's why the majority of people, when you look at 0.09, you're like, nah, I can totally see that difference. So a lot of people will report either the 3 or the 5%. Because when you try them, and we can take a look at different ones that'll do similar types of setups. You'll see it really is within your vision range, but somewhere in that zone from 0.1 to 0.03, it's going to become impossible for you to tell the difference. And it varies by person. So they will usually tell you which one of these they used if they report resolution for modern systems. But if they do not, which one do you think they gave you if they don't tell you?
3%?
Yeah, why?
It's kind of what it is.
It's actually the other way around. Think about where it goes, right? What your modulation transfer function is going to start high and it drops off, right? That's a typical transfer function behavior, right? So when it's giving you that level, it's saying how high is that, right? So at 0.03, it's dropped off more, so it's further out, right? So it's just, they're usually giving you that because they're kind of saying, hey, I'm getting a better response off this. So you want higher frequency range that's still visible, which means you can see to smaller things, right? Because when you go back in frequency, a larger frequency means a smaller spatial area. Smaller spatial resolution is better. Okay. So here's the part that I really want the PDF stuff for. But I realized once I did this, I want to be able to write all those equations down because I didn't want to flip back and forth to the other thing. So these were some very early systems to do this. You can see like a lot of them use line patterns and they kind of have some, they'll set them at different areas. This style is actually still a little bit popular, line 54 here, because you can kind of step down and you'll see it'll blur out. So that one is still a somewhat used. You can kind of see the same thing happening here. A lot of them will give you these kind of up bars so you can tell. They'll give you multiple at the same range. So that tells you when you started a new line pair or spacing on them for them. So those are kind of typical ones. But there's a lot of other ones that are not as heavily used. Some of these ones here where they did both the light and the dark So you can see, was there a difference in how they handle light or dark, things of that sort. Turns out to not be as important. You see in the upper right, that kind of cone, I've got a better picture of them on the other page. You see a little bit of it here as well. There are variants of these that are used today, but they're not, still not as. So these are some early systems to do it. And again, remember, all you have to do is take a look, apply your system to it. So imagine these are all optical, but you can do the same thing with X-ray or whatever. If I took a picture of one of these systems and my system has a blur in it, the really fine details are gonna go and be gone. So if I find the last one where I can tell the difference, right? That one in essence tells me that resolution point for the MTF function that's somewhere around that 3-5% most likely. Right? And so now I know where that 3-5% has dropped to pretty darn, I know the frequency range, I know it's somewhere around 3-5%. I can trace back. Most of the time these are going to be Gaussian distributed. There's a couple other ones that are common. But if you know something about the general shape, you've got a point, at 0 it's 1. So you can now completely define your curve. If your system has other property that might not be perfectly Gaussian and you've got other areas, you can measure it there and just plot those individual points. The lines, spacing, so 1 over that is your frequency, and you can measure the contrast directly. So that's kind of the ideas of these ones here. So this is practically what they look like when they go on. I tried to get an actual one here. This one's used for medical purposes. See, it's in the clear plastic, and it's got basically these are usually done with metal, and then they cut out the shape that's in there. And so when metal really absorbs the heck out of X-rays, and the clear plastic really doesn't. And so basically, you put that straight on, and you can see like X-rays with you. You can see here the effect of, here is one of the phantoms, and you can see with noise. We'll talk more about noise next time when it goes in. But you can kind of see the effects. It's not always the best contrast here, so you have the screen version. But you can see where it goes off, and you can measure the line pairs that are usually labeled above them. And typically people are looking for that point where they can't tell the difference, find the number that's above it, and that tells you that 3-5% zone. This one is one of the lines that's drawn out where I showed you dark, and you got the different patterns going down. Take the image of that, and this gives you a cross section where that yellow one is. This is cross scale. And you can see for these ones, I can find, what was my minimum, what was my maximum, like the difference. And then I take the difference, and then I take, add the two together, the bottom and the top, divide by that. That gives me the modulation at that frequency. Walk all the way down. And you'll continue to see for each one, and calculate that modulation transfer. Make sense? Now notice, do I ever truly get F0? Frequency 0 for this. No. Right? So am I in trouble?
Probably not.
No. Because notice on the very first one, we make it big enough. See how it fully saturates? Right? So you could calculate, what is the max to the min on that one. Right? That's at some earlier point and just straight line it. The rest of the way to the origin. So it's pretty trivial at that point to do. Okay, you feel good? All right. This is just a note. People figured out also fairly early on, you can see these are not aligned pairs, but they're putting a circular array. Why might we want to do a circular array?
Shows things at different angles, and so
Yeah, see, the angles really kind of matter here. And the big one that matters is imagine now they're in a 3D like a CT system. And that's what this one's actually for. This is actually a cylinder. And so you can position it, right, from a couple different angles. The second you go to a grid, the digitized grid is also going to impose. In addition to the system, there's the grid you put it on. So how you rotate this relative to it is going to affect your minimum and maximum resolution. So you can take this and go, oh, it's somewhere in this zone. You can tune it, turn it a little bit, re-image the thing, and you can more precisely home in. But you can see exactly where that is. Well, you know, and it does let you see where the best directions in your system are. So you know you can then tune the finest resolution to your worst direction to find out how that's going to go. And it allows you to get a lot of the different angle patterns. This one, contrast resolution phantom. This is a little bit of an older one, but it's cool as heck. So I believe it's on one of your homework problems too. But the idea of this one was to actually be able to get the modulation transfer function without any work. So you set this off. This is sizes. So as they get smaller, the frequency is getting higher. And the contrast is higher and getting smaller. When you pass this through the system, what's going to happen is it's going to blur things. And you can see there's kind of an edge that people have marked where you can't get off. Now note this one has this mirrored when it went here. So I just picked images off the screen and realized you just took this thing and flipped it over. That's what they got. Right? But you can then draw these lines. So this is low frequency, this is high frequency. Sorry, it's backwards. All right, but if I flipped it, the text would be backwards. And you really want the highest density down at the bottom. If you do this, this line where things disappear is your NTF profile. So if you put this so it was down this corner, kind of rotated it down, and you drew that line curve, you would actually have, for the sizes you were given here, you'd have the NTF transfer. Right? Because where they disappear, you can't resolve that one. So it's kind of a neat function in that sense, right? And it works nice with noise and everything else. You can actually see how the noise will affect the NTF and everything just directly. You just see it, draw the curve, you're done. So that's why I always thought, it's kind of an older one, not everybody uses them, but I actually do think they're pretty awesome. They do have a version that's round that just stuck that one in the upper corner. Right? Again, largest ones on the outside going to the center. You do have to be a little bit careful with that because often with symmetric systems, the resolution will be better either towards the center or towards the edge. And so it can get a little bit distorted by shaping the things in that way. But we'll talk for the individual systems, we'll explain why ones. Usually the center is a little bit better, but that is not always the case. Yeah.
What are the projection angles mean on the images on the right?
Okay, so this is a CT reconstruction. And so imagine you have some depth here. And we'll actually do CT, we'll develop all the math and everything else for them. But basically they're saying the more angles you take, in general, the better quality of an image you're going to get.
So this is after reconstruction?
This is the reconstruction. So you've taken this, which is a 3D thing, you've put it in, you've taken pictures, this one. At 180, it's every 1 degrees. Right? At 60, it's every 3 degrees. And so they take those different measurements and then most likely they then filter back projection, all of their other techniques, and they generate an image. All right, so you can see on here, this is better quality than this one. You can see more streaking. This one was at 30, which means 6 degrees between them. You'll see the streaking pretty profound here. If you actually measure between the streaks, it's 6 degrees. So, but we'll talk more about that when we get to them. All right, so there's some characteristic things you can look at a reproduction and tell exactly what they did. Nowadays, most people don't do less than 4 degrees. just because 6 degrees is just ugly. Anyway, so usually 1, 2, or 4 are the standard numbers people use. You know, and this one allowed there to be noise in it, those ones didn't. And you can see, well, that one is so small. We feel good? All right. And again, the point of this is you can just kind of see the profiles on them, number one, but you can see the effect of other parameters on the system. That's kind of a nice direct measure, give you a visual area. This one just gives you one other one. I mentioned that it gets, if you make the assumption about going towards the center, this one puts it on a radial direction, which usually is not as bad for the variation. So you get to measure the different ones without having the radial direction influence us. All right, so that's kind of what those slides are, just to get you used to some ways people can measure them. Now we're going to pull up MATLAB and start playing with these. I'm going to drag all mine. I've got a MATLAB directory where I stick a lot of different stuff in. Okay. Go MATLAB, go. So if you've already have yours up, the first one I want to take a look at is this resolution example here. I was like really impatient. Okay. Close that. All right. I'll load all of them just so I can have them here and then just run them. Okay. All right, so pull up resolution example. It's a pretty straightforward little setup here. You just pick a number of points, that's what n is. All right, d is 1 over that, so it's just stepping by a small increment. The reason why I've got 101 here is to go from 0 to 1 has that one extra one. So this is going to be divided by 0.01 steps. So that's why I did 101, just to count for the end. And then what I've got is basically, in this case, we're going to take a look at a series of ones. The first one here is going to be a linear function, where it just goes from 1 down to 0 across that distance. And we'll take a look at that. Remember that first area I was saying about if we were doing the full width half max, how straight does it look? Can you tell from the profile? That's what this is going to do. So we'll do a linear, and then I've got like an exponential and a Gaussian, stuff like that. So just run this one. And depending on how fast MATLAB is, we'll see our results. Okay. So reading this, the green line coming down, dashed, is this is kind of the center of the distribution. That's the green line coming down is the right side. All right, and then we said we kind of took the left side, we put another one over here. So this is the center of the second one, then they slid down. I tuned its shape, not too hard on linear, all right, so that they're going to meet right at that point, the area. So the distance between these two is full width half max. That's the important area for that 0 to 1. And then I added the two together, and you can see it is straight across the top, that red line. That's the effect of the two right next to each other. you know, if I had two objects, one here, and it had this kind of linear cone shape, you would not be able to tell at full width half max. This is the definition of you cannot tell there are two objects here. It would just look like one, right? And you can see that, right? Totally flat. So I did the key press thing, so all you have to do is click, and you'll get the next one. So this next one here is a Gaussian. It's on, right? I thought I did exponential next. I did. You guys clicked once you got Gaussian?
Yes.
Okay. So I guess I put them out of order and didn't realize. So this is a standard Gaussian. You can see the bell-shaped curve at the halfway point. So again, this is a Gaussian blur, very, very common that's out there. Anybody know why Gaussian blurs are so common?
They don't really have Fourier transform properties.
They really do, don't they? Right? What's the Fourier transform property of a Gaussian? Another Gaussian, right? So that's kind of a cool feature, right? So in a sense, it's the fixed point in Fourier space, which talks about diffraction limit. So when you talk about light, where everything's kind of being diffracted by little tiny particles and stuff, as you're going through, this literally is the one that returns the same distribution. So in that sense, everybody's heard of Heisenberg uncertainty, right? Is everybody familiar that the Fourier transform is a great example of Heisenberg uncertainty? Right? So if you think about it, if I had a really small rect function in space, its transform is a really wide sinc function.
Right.
And as I made that rect function wider and wider, what happens to the sinc function?
Smaller and smaller.
Right? So in space, if it's small, it's large in 1 over space, i.e. momentum area. Right? And as it gets bigger, it goes the opposite. And it turns out because of the shape and how it drops off, there's a little bit of variance, a little bit of uncertainty of what that trade-off is. Depends on your function shape. Gaussian is at the optimal point. It is where you hit the quality on Heisenberg uncertainty in the Fourier sum. So if you're any transfer function other than a Gaussian, you have uncertainty. You're a distance away from optimal. If you have a Gaussian, it's optimal for the space. And the universe usually optimizes. Okay? Much the same that the reason why exponentials are so important in the world is because it's the fixed point of calculus. So too, this is the fixed point of the Fourier diffractions, and away you go. But notice, even with this, because it hasn't dropped off to 0, right? So it gets kicked up a little bit. So you actually get what looks like two humps. It looks like they're closer together, but you can absolutely tell. Oops, I just accidentally clicked, which is the next one. But if you could tell on yours, just don't click yours yet. See how you get that height differential, right? You could totally tell those were there. They would look closer than you thought, but you would still be able to see that there were two. Right, and that's at full width, half maxing it. So if you look at the spot where it was, I adjusted them to hit. All right, I did the same thing over here too. I got as close as I could. I played with the numbers a little bit on the exponential decay to the point where it was kind of tedious, right? I got to 0.49. I felt that was close enough. But if you look at this one, notice how high it is on this side, right? Obviously that's still 1, but over here it's over 2, right? It's almost 0.25. So you still get this strongly bowed, right? So even though this is at full width half max, because it didn't drop off to 0 fast enough, you actually get an apparent difference between the two. So full width half max does not define the resolution for Gaussians or for exponentials and a host of other ones. It works great on linear. But linear is not a common profile. It's not an impossible profile, it's not a common profile. So I just mentioned that those tails, very often you will get tails that will continue out for a while. If it's got tails that continue for a while, you're more than likely not going to get a good behavior out of full width half max. That makes sense now. Why, it kind of makes sense. It's a nice, cute approximation. When people hadn't really thought through it, it was a great way to go, but it's not a great way to go when we put a little bit of thought into it.
So the idea here is you could have these two objects closer together and you might still have a divot to tell them apart?
Yeah.
Is that okay?
Because this is the distance of full width half max. And what you would see is that red profile from above. Right? So you would have higher on the outside, it would be a brighter, and it would be a little bit darker in the middle. You would see it. All right, we feel good? All right, so that's all that I'm trying to show with this one, is to just get you to see those. Plus, it's just kind of helpful to see how you can calculate some of these things very, very easily. Right? The profile for a lot of these, right, calculating exponentials are really simple. So just get comfortable doing a real quick and dirty simulation. It builds intuition. Most of you have seen the equations, have done the formulas. Those are good. You should absolutely do them. Try to build some intuition too. Actually, before I go to the resolution example 2, let's take a look at this point spread function versus line spread function, which we've talked about. There's a bunch of different ones in here. We'll walk through each one of them, but let's start with Gaussian. So just take this one and run it. Oh, thank you. Now what you're going to see here is you'll see a red and a blue. And if you notice here, the red and the blue are right on top of each other. So this is the point spread function, red, and the blue one, which is on top of it in phantom line, like long, short dash, long, short dash. So that phantom marking of the cyan or blue is the line spread function, a profile through. So it's worth noting that the difference between the point spread function and the line spread function, if you are doing a Gaussian, is nothing. There's another nice feature about it. So it turns out, if you calculate the line spread function, you've got the point spread function for a Gaussian, which is a very common distribution that's out there. Another awesome behavior of Gaussian functions. Now, the next one, we're going to click and we're going to see something else. What you'll see on this one is actually what you would measure if you set up a point spread area and you had a single point, and what you would do if you had actually calculated a line and calculated it. You'll see the strength of the signal. So the red is the strength of a signal if you did it from a point. So I took the point spread function and I just applied it directly to a single point on here, and this is the value of the function that I got out, assuming I could make a floating point. That's how strong the signal would be coming out. If you look, this is blue and green because there's two different lines. Okay? I'll explain what each one does, but let me first just do the line one. All right, you get this line if you had a line and you measured it. Because when you have that spread function and it hits a line, right, you get the point spread function. Part of the effect of here carries down to the next area, right? And it'll affect all the measurements all the way down and all the way up around. So they add to each other. So in essence, you're going to get, in addition to this, that's somewhat proportional to the length of that line, which is what you're actually seeing on this. If you took a look, right, it's 20 some odd. If you take a look at the code, that's pretty darn close to the actual 25, which is the radius. And this is pretty darn close to 1, and that's pretty darn close to the radius distance, I mean how wide the image is from the center added onto it. So that's a huge difference in signal. So your noise is going to be constant. So if you've got any decent amount of noise, this signal is probably gone. And even if it's not gone, anything you're taking off here is probably useless. Whereas if you're measuring that one, your signal is so much stronger. Right? It's going to be at least 1 to 2 orders of magnitude stronger. That's why even if you can do a point spread function, you don't want to do a point spread function. A line spread function is even better. Now there's 2 colors here. Right? You can see the blue and the green. One of them is the line spread function I mentioned. Draw a line and away you go. The second one is an edge function, or related to an edge function. An edge function is, imagine I just took 2 of these, I made 2 halves of a plane. And one side I made dark and the other side I made light. When you apply the blur, it's going to blur this whole thing. Right? But now there's tons of stuff affecting it. So it's actually gigantic. It's about another 20 times taller than this one is. The way an edge relates to a line, well, let me ask you guys. Right? Consider a profile through an edge. What does it look like? So if I were to just cut this, turn it sideways and look at it, what would the profile look like?
It's almost the same.
A step. Right? So it's a step function. If I were to take a line and cut it through and draw it, what would it be? It'd be an impulse. How do these 2 relate? Derivative. Take the derivative of this, you get this. So all I have to do for this one, which is really stupid easy to make, and it gives you a crazy strong signal, is take a really crazy strong signal and take its derivative. The easiest way to do a derivative in a discrete system is take the difference of successive ones, and that's all I've done here. This is just the difference between successive pixels on one of these edge spread functions. Notice, they're right on top of each other. But the difference would be, right? This one is about 1. Green one's somewhere around 20 some odd. And the other one started at like 400 and something, and then I took some differences. But the original measurement was so much stronger, and I just have to make sure I suppress my noise. But I got the least noise on that last one for the edge. So which one would you route it to? Yeah, the edge. Right? And then take the difference. Right? It's going to give you the strongest initial signal, which means you'll get the initial measurements, and then you just be very careful with your math, and you will get good values. Yeah.
So are these just helpful for kind of characterizing your image system?
Yes, because you have to be able to characterize your image system to improve it.
Okay.
All right, so one of the first things you have to do is know what does it actually do. What's the net effect of it? And this will tell you, does it amplify, does it blur, is there a problem, right? So every day, hospitals have to run through these phantoms and recalibrate their systems. It's done every morning on any medical system, right? This is why you have to have medical physicists and stuff like that. Some systems you can go multiple days, it depends on where it's at, but they drift out otherwise. And you can actually tune them to get these back into the correct profile, which guarantees you're getting better images. And then we will base our corrections on knowing this information. Right? And so we can assess them, and if you make an improvement and you find out, oh, the modulation transfer function improves, you can give a great way of comparing them. It's like if you had to buy 2 systems, how do you tell which one is better? You take a look at the profiles and away you go. All right, we feel good? Okay, so everything is nice and pretty with Gaussian, which is kind of what we'd expect. Let's take a look. Cone was kind of our linear one, right? I take the linear profile and spin it. There wasn't an F special because it's not used all the time, but I figured we did a linear. So I just wrote my own thing to generate a spun cone, right? It's nothing fancy, so don't sweat it, right? You're welcome to look it on your own. It just literally calculates the cone profile and puts them. So we're just going to do that same exact calculation here for a line. So you can see The red is your cone. When I do the point spread function integrated down to get the line spread, notice it's no longer the same. It's really close, but it's not the same. Because again, it's in a cone area. So by the time you hit this outer part here, there's only a tiny amount of cone left. That's why it tends to be very low down here. Up here, there's the cone plus the cone's coming back in space. Right? So when you integrate it up, there's other nearby stuff. So it's going to overestimate. So it's higher on the top than the bottom. But again, it's not too bad an approximation. And you can undo it. Again, if you know the different directions, you can use things like filtered back projection. You can undo this curve. But that is the difference between line spread in the blue here and the red. So if you click it again, you will also see the difference. Notice red, this is what you would get measuring point spread. And you'll see the blue and green still overlap them exactly even in this case. So the edge version, taking the derivative or difference, essentially is the same as doing the line directly on it. Right? So the blue and the cyan and the green are exactly overlapping each other. Just showing that, again, no difference with edge and line. But you get a far worse signal if you're down here. 1. And notice here it is really quite high. I did get the full 25. And you can see that 25 up here, that's the radius. I set it on. So that's kind of the upper limit of where it can go. Just to see it really strong, take a look at, let's say, a disc. We're going to comment this one out. Notice again the red, this is what side profile of a disc. But when you do the line spread, through the disc, it's widest at the center because it's a disc. Okay? By the time you get to the side, it's, you only get one line's worth. So it drops off very quickly. So you kind of get this bullet shape out of it. But that is literally this is how thick it is through the disc. So this is one of the more strongly diverging shapes between point spread and line spread. And it might look like point spread has the advantage here. But when you look at what happens when you set up the area to measure the point spread versus the line spread, I notice the line spread is up at twice the radius. Right? Very, very strong signal for that disk. Whereas you're still down at 1 for the actual disk itself. There is no area where a point spread function ever does a good job. Right? At least as far as we're concerned, trying to figure out what the system is so that we can actually control it. And that's always the first step in any good control problem, is you have to be able to do system identification. So this just shows you this is the correct way to do identification. I'll leave the final one for you, the averaging, just because, it's easy enough to run and I don't want to waste a whole ton of time. So I took these same ones, the resolution example 2. In this one, I'm just going to take these ones. We've now felt comfortable about them. This k equals 9 is going to tell you how many pixels apart they are. Roughly speaking, I tried to make it for the Gaussian by picking this S to be 8.4. The distance between, the limit that's, say, like somewhere around 10% is right around 10 pixels apart. So this is going to be the distance, in essence, between the blocks. So you'll see in a sec when you run them. But this number is a number you can change, and you can pick whichever one you want to use. But 10 here will get you down to about the distance for a 10% signal. So if you run it, This is what it actually builds. So it just builds a bar phantom. The width of each one of these is 10. And then it runs the appropriate filter. This is a cross section right through the middle. It runs the filter, the Gaussian filter for it, and this is what you get. So this would be the equivalent of a measurement at MTF10. Right? Not because it was 10, but because literally at 10 you can actually measure for just a single one of these, and you'll see what you could do in the previous one if you feel like it. You could set up those same numbers in here, which is all I did on mine. And I found that I got to, at 10 pixels out, I was pretty close to 10%. And you could see at that point, I'm at 96% of the signal strength. So that's telling you it's less than 4% difference in the shading, right, of the effect in between them. Right? Now again, when you're doing that MTF 10, it doesn't mean the two coming together is going to give you 10, right? It means that one has dropped off to 10% at that relative distance. And then you put the two ones together and normalize them, and you get this. And it just shows at the midpoint, right? So we made it so that at the extreme edge, it was down to 10%. So by picking the edge down to 10%, the middle is less than 4% off. Right? So the MTF10 is doing a fairly good job. Right? You can still see it. Right? If you look at that image, see how you could kind of see that bar in between there? Now, if you set this down even a little bit, you should notice it starts pretty rapidly becoming hard to see. Right? So this is down 1, and dang, I can't see the difference. And if you look at this, it's really flat on. So for that Gaussian, just slightly less than 10%, pretty much impossible, at least for me to tell the difference. I don't know, maybe some of you have incredible contrast, but pretty darn subtle. Now this is based on, this is the standard deviation of that Gaussian. Again, you can plot that point spread function if you want to see exactly what it's getting. Plot point spread function. So n plus r, those are just constants I have in here. That's pretty darn close to the middle. I think n plus r plus 1 is dead center. And then I'm going to take the entire cut section. So this is just plotting a cross section. I did 3 at. Oh, it's n by n. Oops. So I need r plus 1. My bad. It's a smaller function than the bar image. So that's the center of the point spread. So you could see this one. If you kind of walked along this line, so it would say at 16, right, and the other one 36. So it's saying somewhere around 20 is the full width half max. So if we were to take this same function and put 20 in, which is full width half max, has the separation between the two. Are you able to see? No, can't be. Okay, so we can see, in cases like this, it just full width half max does not do a great job. It's got its place. It's a useful general guide, but it's really measuring at the middle rather than getting the full size of the spectrum. And in this case, because of the tail and everything, it's pretty darn easy to see that difference. Right, and we just measured it right off the point spread function, so it's as fair as it gets. If we tried a couple other ones in here, all right, so again, you could see, right, this is with a more cone type area. Again, on the line spread, it integrates down, so even a cone is going to get spread out a bit. Notice it is significantly higher on this one. The cone is also not exactly the same width as the other one, so we would have to plot the point spread function just like we did before to calculate where that spot's going to be. Come on, come on. Come on, where's 13? Okay, 38 roughly, 14. So even on this one, it's not doing that great of a job. 20 some odd. We should have a pretty good knockoff on that because that's the point spreads area. I think it was 4. So let's see what it. Yeah. So when we go to 14, which is pretty close to its, right, it knocks them off fairly well. It's not perfect, but it's pretty good. Right. Again, it's not going to be a perfect equivalent of a cone because of that kind of down spread, but it does give you a good measure of it. All right. Do we feel good with how we can use these? So again, the book will show you, right? So to get the line spread, they'll just integrate the y direction. That's simple enough. It's a straight integral. Right? Modulation transfer function, again, take the Fourier transform absolute value. Make sure you normalize 0 to 1 and away you go. Other than that, that's the basic ones on here. And then I would again suggest from that modulation transfer function, you're better off finding the 0.1 level and finding what that frequency is, then 1 over the frequency, or 0.05 or 0.03. And you can try it on any one of those. All right. Have a good day, all.
Thanks, Dr. Stewart.